Wood as a renewable and energy-efficient resource. Imagine a world where we use materials to build our homes, schools, and workplaces that could be grown and regrown, that stored significant amounts of carbon that helped keep our atmosphere clean, and that were less energy intensive in the extraction and manufacture compared to alternative materials. Wood is one type of material that can do just that. And so today, we're going to look at wood as a renewable and energy-efficient resource and compare it to a number of other types of natural resources, such as iron and copper. Let's start with renewable and non-renewable natural resources. Renewable resources are those that can be used and replenished in our lifetime. The wood from our forests is renewable, the oxygen we breathe is renewable, and the solar radiation from the sun is also renewable. Let's take wood as an example. Trees can be harvested for wood and made into products that we use every day, such as framing for our houses, furniture in our homes, and the paper we write on. For some great examples of renovation projects, buildings, and furniture made from responsibly sourced wood, search online for Planet Ark's campaign, Make It Wood. These trees can then be replaced through replanting seedlings or regenerating naturally from seed. Once these trees have matured over several decades, they too can be harvested, ensuring an ongoing supply of wood for our society. While renewable resources can be replenished in our lifetimes, some are susceptible to being depleted if overused. Australia's sustainable forest industry ensures the quantity of wood harvested from forests is less than what can be regenerated, so future generations do not go without. Look for the Australian Forestry Standard or the Forest Stewardship Council certification to make sure you're buying wood and wood products from a sustainably managed forest. Non-renewable resources, however, are those that cannot be replenished in our lifetime. More specifically, it's when human consumption is greater than the rate at which the resource can recover or renew within the environment. Minerals such as lead, gold, and copper, fossil fuels such as coal and crude oil, otherwise known as petroleum, and natural gas are all non-renewable resources, as they generally take millions of years to form. They are formed from the decomposing organic remains of animals and plant material beneath the Earth's surface. These non-renewable resources are often used to create plastics, including drink bottles and grocery bags, electronic goods such as your mobile phone and iPod, and even the plastic ballpoint pens you use to write with. A good way of remembering renewable and non-renewable is through what we call a Penn balance scale. For renewable resources, the Penn weight favours replenishment, representing consumption being less than the rate of renewal. In comparison, the Penn balance for non-renewable resources dips towards consumption, outweighing the rate at which they can be renewed, and therefore continuing to use them like we have is unsustainable. Let's consider how some of these natural resources are used and the energy that is required to extract and process. All natural resources, renewable and non-renewable, are in their raw state. Once the raw material has been extracted from the Earth's crust or harvested from the surface, they are processed into goods that can be used. For some natural resources, the amount of energy required to extract, melt, and cool the material is significant, and so must be considered when looking at the overall impact of that material in terms of environmental sustainability. For example, iron, which is commonly used in the production of steel, is a metal mineral that is extracted from the Earth's crust in the form of iron ore, and then refined through the process of smelting. The smelting process is energy intensive, as high temperatures are required to drive the chemical reactions to separate the iron from the iron ore. This is done by adding carbon, or coking coal, which allows the oxygen in the iron ore to form a bond with the carbon, leaving a metallic iron. According to Australian CSIRO researchers, in 2012, steel production was responsible for an estimated 1 billion tonnes of greenhouse gas emissions, and contributed to around 7% of all carbon dioxide produced from fossil fuels. Copper is another metal mineral which undergoes a similar process. Copper production is responsible for around 0.2% of global CO2 emissions, and copper alloys are used in many everyday products, such as mobile phones, computers, electrical gadgets, gutters, pipes, and even taps in your homes. So whilst metal products can be recycled, the raw materials required for production cannot be regenerated in our lifetime, and the process of extraction is energy and carbon intensive. Cement, commonly used in construction, is another material that requires a lot of energy to produce. It is a compound comprised of oxides of calcium, silicon, and aluminium, and is used to make concrete by mixing with crushed limestone or granite rock, sand, and water. CSIRO have estimated that cement is responsible for 8.1% of global greenhouse gas emissions produced from fossil fuels. Wood is very different to the iron, copper, and concrete examples we have used. In Australia, trees are deliberately grown and regrown in plantations or in native forests for the raw material wood. The only energy inputs into native forest harvesting systems are the fuels used by harvesting machinery and log trucks, and equipment used in artificially seeding areas where natural regeneration is unlikely to be sufficient. There are generally no fertilizers, herbicides, or insecticides used in native forest systems. In plantations and agroforests, woodlots on farms, improvements in soil cultivation and early management, silvicultural techniques, along with tree breeding, genetic science, has driven a dramatic increase in the amount of wood able to be grown and drawn upon for a whole range of societal needs. When trees are harvested, the wood is taken to a local timber mill to be processed into a wide range of products, such as timber flooring, frames for housing, telegraph poles to hold electricity wires, paper to write on, furniture for our homes, and many more things. Mill waste, including sawdust, can now be used as a biofuel to fuel boilers, which produce heat that can be used for drying timber in kilns. Excess heat can also be harnessed to produce steam and run turbines that generate additional electricity. Have a look around you and see what products are in the room that have used wood, copper, steel, and concrete. Compare if they are renewable or non-renewable, and how much processing has gone into making them. Now let's consider the energy used from cradle to product. We have mentioned several times that energy is needed to extract or harvest natural resources and process them into usable goods. Energy is also used in the construction of finished products such as school buildings and houses. The total energy used from cradle to product is studied through life cycle assessments. The sum of the direct and indirect energies of the individual stages along the value-adding chain is the embodied energy. Let's compare the energy used through the life cycle of some renewable and non-renewable natural resources. To start with, we need to understand that the law of conservation of energy states that total energy is maintained in energy transfer and transformation. Energy is neither created nor destroyed, and it can be in the form of potential, kinetic, or chemical energy. With this in mind, it has been estimated that the amount of energy required to extract or harvest, process, transport, and install natural resources into building materials is around 30% that of the overall life cycle energy. This 30% is otherwise known as the embodied energy. A study looking at embodied energy figures for an average-size home of 200 square meters in a warm, temperate climate showed a wooden-framed house use 651 gigajoules of energy to complete, compared to a steel-framed house using 764 gigajoules. That is 17% greater energy. If you then take into account the energy benefits from using biofuel in wood processing, the steel-framed house needed 281% more energy than the wooden-framed house. Wood is also a better thermal insulator. Therefore, it takes less energy to heat and cool houses that are internally clad with wood or wood composite materials. What can we do as consumers? Human consumption patterns do impact global systems and the atmosphere. We are currently consuming the world's natural resources at a level needing 2.4 planets by 2050. We need to consider what impacts the products we buy every day have on our planet. How can we contribute to a more sustainable future? Choose your products wisely. Think about every time you buy a new phone, computer, iPad, what metals are required to extract, melt, and cool to produce that new product. Substitute non-renewable products with renewable products. Choose the wooden table over the steel frame table, for example, or the wooden ruler over the metal ruler. We can look for certified wood products to be used in our homes, products, and materials. It's even better if it's locally sourced wood, as we can minimize transport and energy requirements. Finally, think about avoiding, reducing, reusing, and recycling. In summary, renewable natural resources can be replenished in our lifetime, such as wood, wind, water, and solar energy. Non-renewable resources cannot be replenished in our lifetimes, and the rate of consumption will exceed renewal. They include the fossil fuels coal, natural gas and crude oil, and minerals such as iron and copper. Wood requires less energy to produce and use in construction than the alternative materials steel and concrete made from non-renewable resources, and is a more energy-efficient building material. A sustainable future depends on everyone substituting non-renewable natural resources where possible with renewable resources, and producing less waste. Give it a try. For more about our forests and wood products, visit forestlearning.edu.au.